All right, let's look at an example of a buffer calculation. So we're just going to use a generic example. We'll look at some more specific examples later. So let's say, what is the pH of a buffer made by mixing 1.00 liters of a 0.020 molar weak acid, which I'm just going to call HA, with 3.00 liters of a 0.060 molar conjugate base. So that's the conjugate base of whatever this weak acid was. And also I'll tell you that the Ka of this weak acid is 6.3 times 10 to the negative 5. So again, it doesn't matter what the formulas are, what the names are. A lot of these weak acids and their conjugate bases that we use for buffering systems are not common, and don't get confused or worry about those. You just need to know that it's the weak acid and its conjugate base, and you need the Ka of the weak acid. So this also has a little bit of calculating that we need to do because we are making this buffer. So we have 1 liter of a 0.2 molar weak acid, and then we have 3 liters of a 0.060 molar conjugate base. So we have 1 liter and 3 liters, and we're pouring them together. So we're making a new volume because we had 1 liter and 3 liters, we're pouring them together. So what we need to do is we need to figure out what the new concentrations are, because the concentrations are going to change because the volumes have changed. So anytime you're doing a problem that has multiple steps, it's good to have a plan. I always write out the steps that I'm going to take. So the first thing that I'm going to do is I'm going to find the initial concentrations. Of the weak acid and the conjugate base, because these concentrations are going to change once we mix them together. Next, we are going to use an equilibrium table to solve for X. So this is a weak acid ionization. But the difference is we also have an initial concentration of conjugate base. We have weak acid and conjugate base. I'll show you what that looks like. And the question is asking for the pH. So we're going to use the concentration of hydronium at equilibrium to solve for the pH. Okay, so first let's find the initial concentrations. Okay, so this is just a dilution because we have a concentration and we're going to add it together. We're increasing the volume. So we're changing the concentration by increasing the volume. This is just a dilution. So I'm going to say for the concentration of my weak acid, remember this is just M1V1 equals M2V2. And we are solving for M2, final concentration. So I'm going to say my initial molarity, 0.020 molar, times my initial volume, 1.00 liters, equals my final molarity, which I'm solving for. My final volume is going to be 3 liters plus 1 liter, 4.00 liters. That's my final volume because I have these two volumes, I'm adding them together. So I'm just going to divide both sides by 4.00 liters. And I'm going to say that M2, the initial concentration of my weak acid when I start this equilibrium, is going to be 0.0050 molar. So now let's do the same thing for the concentration of the conjugate base. M1V1 equals M2V2. Again, we're solving for M2. So 0.060 molar this time. That was my initial, the concentration of the A minus, times that volume, 3.00 liters, equals M2 times my final volume, which is again 4 liters, because I'm going to add the two together. M2 is 0.045 molar. So the initial concentration, once you add these two together, for the weak acid is 0.0050, and then for the conjugate base is 0.045 molar. So that's the first step. Find the concentrations after we mix these two things together. So now let's use an equilibrium table to solve for X. We're just going to write this as a weak acid ionization. So I'm going to write the equation, HA plus water is in equilibrium with the hydronium ion plus the conjugate base. So now this is a little bit different than some of the other problems that we've done, because now in this case I'm starting with some of this. I'm starting with an initial concentration of A minus of 0.045 molar. My initial concentration of my weak acid is 0.0050 molar. Again, water doesn't contribute, and I don't start with any hydronium. So now I'm just going to solve this like a regular equilibrium table and solve for X, which is my concentration of hydronium at equilibrium, to solve for the pH. So this is going to be minus X, 0.0050 minus X. I did not need to put the concentration here. It's always in molarity, so I didn't need to show that. Plus X, X, plus X, X. Sorry, 0.045 plus X. Okay, so now this row right here is what we use with the Ka of this generic acid. So I'm going to say 6.3 times 10 to the negative 5 equals X times 0.045 plus X over 0.0050 minus X. We are going to get rid of the X. We're going to always assume X is negligible. For these buffer calculations. So we are going to say 6.3 times 10 to the negative 5 equals X times 0.045 over 0.0050, and we are going to solve for X. So I'm going to take both sides times 0.0050, and then I'm going to divide both sides by 0.045 to solve for X. And when I do this, I get X equals 7.0 times 10 to the negative 6th. So remember what this is. X is not the answer. The answer, the question is asking what is the pH. This is not the pH, this is X. X is the concentration of hydronium at equilibrium. I just want to show you, even though we assumed X is negligible, even though maybe this relationship was not less than 500, let's check. Divided by 6.3 times 10 to the negative fifth. Yeah, so this number, this relationship is less than 500. But let's see this number, X, let's see if this changes it. So 0.005 minus 7.0 times 10 to the negative sixth is still, with the correct number of significant figures, 0.0050. So even though the assumption that we have been using, where this relationship between the initial concentration and the initial concentration in the Ka was not greater than 500, you always can assume it and then go back and check to see if X actually did change it. And in this case, you see it doesn't. So that's why we assumed X was negligible. You don't have to. You are always free to use the quadratic formula. If you would rather do that, you will end up with the same answer. Okay, so this is X. X is the hydronium ion concentration. So now we are going to use the hydronium ion concentration to solve for the pH, which is what the question asked. So I'm going to say the negative log of the hydronium ion concentration equals the pH. So negative log of 7.0 times 10 to the negative sixth equals 5.15. So remember, because these numbers both have two significant figures, my pH needs to have two decimal places. So the pH is 5.15. So that is the pH of this buffer as it is made with these volumes of these concentrations. So you know that this is a buffer problem. So if you're doing an example like this in SmartWorks or on an exam, it might not say what is the pH of the buffer. So we've collected quite a few different types of calculations that we're doing now. And one of the major problems that students have is they're able to do all of these types of problems when the problem tells you what type of calculation it is. But for example, if you were reading this on an exam and it said, what is the pH of a solution made by mixing this with this, you would know that this was a buffer calculation because it's a weak acid with its conjugate base. That's the only type of calculation that we do with both of those. That is a buffer because, you know, by definition, it is resisting change in pH because it's made up of a weak acid with its conjugate base. So this is an example of a buffer problem, just a generic example. We found the new concentrations, we put those into the equilibrium table and solved for the pH.